In this video I'm going to show 3 different methods for configuring the SilverHat DCC booster. Hello everyone and welcome to the IoTT channel. I am Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I'm happy you made it here and thank you for your support of my channel. To get started, let's have a look at the 3 different work modes of the SilverHat boosters as shown in this table, the available features and what can be configured in each of the work modes. The basic mode is just the booster software on the Arduino without additional IoTT stick. In this mode, the only way to talk to the booster is via USB port on the Arduino. The DCC mode is adding an IoTT stick but only connecting the DCC input to the booster. The booster has a 2-pole connector for this purpose and it can receive any track voltage up to about 24 volts. In this mode, the booster can receive switch and signal commands via DCC, which can be used to control track power and polarity. And the Loconet mode is if the booster is equipped with an IoTT stick and connected to a Loconet system. In this case, it can receive the DCC signal and commands from the Loconet network via one of the Loconet connectors, and it can report back to the network in case of overload or short-circuit conditions, so it supports bidirectional communication. Independent of the mode, all configuration data is stored in the Arduino EEPROM, and here is the memory map overview. It starts with a section for the configuration data for the booster device data, so data that is applicable independent of individual booster channels. And then there is a section with configuration data for each individual channel that is installed in the booster. Remember, the SilverHat can support up to 6 track outputs with up to 8 amps of track current each. And as we see here, each of these channels has some channel-specific configuration data. Now, the EEPROM size of the Arduino is 1024 bytes, but the memory map shows addresses that go beyond that. How can this be? Well, the reason is that I kind of created a virtual address table for the communication with the booster, which then internally is mapped into the physical memory space of the Arduino. Those addresses are listed in the right column for your information. The ones that are important for configuration are the virtual addresses listed in the first 2 columns. If you find this confusing, don't worry, as I created some tools to make configuration really easy and you usually don't have to care about memory addresses at all. So let me show you the ways that are available to easily configure the booster. If you are running the booster in basic mode without an IoTT stick, you can hook up the Arduino to your computer using the USB port. You then can download the offline configuration tool from the GitHub link in the description below and save it on your hard drive. Then open the index.htm page in your web browser, which brings up the same configuration and control screen you would get from the IoTT stick. Click the Connect button next to the IoTT icon and then select the serial port that is connected to the Arduino of the SilverHat booster. As soon as the connection is established, the input fields become available and you can edit the pin configuration as explained in video number 134. Changing to the Options tab, you can set nominal current, fuse and reset mode and enable auto reset if the booster channel is equipped with the Revision 5 PowerShield board. Of course, what is not available while in basic mode are the settings for actuators and reporting booster status via Loconet, as this would require an IoTT stick for the communication. You then can switch to the Monitor tab where you have the basic control functions to turn track power on and off, reset the booster after a short circuit, and change the polarity of the auto-reverse outputs. And of course you also have the amp meters displaying the current flowing through each booster module. If you add an IoTT stick, you can use the DCC and Loconet modes of the booster. In this case, the USB communication is no longer available since the serial port of the Arduino is now used by the IoTT stick. Instead, you can connect to the stick via Wi-Fi and make use of the many additional features provided by the stick. On the node configuration page, you select SilverHat as hat module. Then you can use the command source drop-down to select the mode. Select DCC interface for DCC mode or Loconet interface for Loconet mode. As always, click Save and Restart to save the settings on the stick. To access the SilverHat configuration screen, simply click the SilverHat tab and the SilverHat configuration page is loaded and populated with the current configuration data. The page is identical to the one shown before, except that it displays the additional configuration options for actuators and reports to Loconet in the Options tab. And also in the Monitor tab, it has the system power buttons if it is connected to a Loconet system. Watch video number 134 to see in more detail how these options are used. So, whether you are using an IoTT stick or not, the booster can be configured with the same graphical user interface, although connected in different ways. And this interface is what I expect to be the standard way for the SilverHat configuration. However, there is a third option which is only available in Loconet mode, so when the SilverHat is using an IoTT stick and is connected to a Loconet command station. In this case, it is possible to send the configuration commands over the Loconet cable using the SV configuration command set. SV or system variable commands are similar to decoder CVs, only that they are for other devices than decoders. They are supported by several smaller device manufacturers, but to my knowledge were never implemented on any Digitrax product, as they typically use op switches for the configuration, which is a similar concept but using different Loconet commands. SV programming is supported by JMRI though, and in fact it is possible to manipulate the booster memory map from JMRI using SV programming. Open the single CV programmer window from the JMRI tools menu, then select System Variable Type 2 in the lower part of the screen and enter the Loconet address of the booster. By default it is set to 1234. Now you can enter a memory location of the booster and click the Read button. The value is then displayed in the value field. If the memory location does not exist, the display line will show a value of 255. The same way you can send a write command to a memory location. In this example I send a 1 or 0 to memory address 241, which according to the memory map turns the track output of all booster modules on or off. And here we go. I send a 1 and all boosters set the track power on. I send a 0 to the same address and the track power goes off on all modules. The SV protocol as defined can do a few more things than what I currently see implemented in JMRI. In particular, it has a command that reads 4 memory locations in one single command. I tried this in JMRI, but I was not successful. Maybe it can be done, I just don't know how. Anyhow, to support this method, I added a simple SV programmer to my Node-RED Loconet suite, which works using Loconet over MQTT. Here it is possible to query Loconet for devices that support SV programming, then select the device from a list of available devices and send read and write commands for either 1 or 4 memory locations. The data fields are then populated accordingly. So if you want to use SV programming, you can use the Loconet tool suite for Node-RED from my GitHub page. The link is in the description below. I have updated the code and you can simply import it into your Node-RED application. Don't forget to activate the MQTT gateway on the IoTT stick to make sure the Loconet commands are available in Node-RED. And that's it for this video. I hope this information was useful or at least interesting for you, and I gave you an overview how you can configure the SilverHat booster to meet your requirements. If so, please use the comment section of this video to let me know your thoughts and click the like button below. That is an easy way to show your support for the IoTT channel and to promote this video to other model railroaders because YouTube likes the likes. Thanks for watching and see you in the next video. Now, as mentioned before, unless you want to write your own code to access the booster, all this is just informational. You don't have to deal with this interface at all. It is still good though to know that they exist, just in case you want to directly manipulate some booster settings. And so here is a quick view of the complete memory map for your reference. First, the device data. Here we have the number of booster channels installed in the device, an activation flag for external communication, and the device address. In a Loconet environment, this is also the Loconet address. In the other modes, the address is just set for internal communication purposes and you don't have to worry about the value. Then there is 1 byte for the power-up status and the accepted signal types, either DCC or PWM. PWM, which could be used for boosting DC districts, is most likely going away as it does not really make sense to have it. Finally, there are 2 activator definitions to remotely power the booster track output up and down. Each activator consists of 1 byte for the input type, for example a switch or signal command, and the input status, either thrown or closed, and 2 bytes for the 16-bit address of the actuator. As explained in the last video, it is possible to have different addresses for switching track power on or off, but in most cases we probably just use thrown and closed of the same switch address. The highest addresses in the memory map range are reserved for command input via the configuration interface. Sending a value to these addresses causes the booster to report some operational data. Address 240 is to get the current status of the DCC input. 241 is used to manipulate the track power status for all booster modules of the device. And writing to address 255 causes the booster to report the entire device configuration to the serial interface. The column to the right, by the way, shows in which mode the data or command is available. Actuator commands, for example, are only available in DCC and Loconet modes, where an IoTT stick is installed that can interpret these commands and initiate the desired action. A similar table exists for the booster channel configuration. Here we have the pin settings and the amplification rate for the current reading. Note that it is multiplied by 100 to avoid a floating point data type. Then we have auto reverse mode and auto reset mode, which can have individual settings for each booster channel. Next are the fuse settings and the nominal current of the booster. As explained in video number 134, the nominal current is internally used to calculate the short circuit trip current and to manage a temporary overload of the booster. The next entries from 8 to 26 are used to define external actuators for power on or off, auto reverse polarity, and for resetting the booster channel after a short circuit. All these actuators are available in DCC and Loconet modes only. Finally, there are two more actuator definitions which are used for reporting a short circuit or an overload situation back to the network, and therefore they are only available in Loconet mode where there is bidirectional communication. Similar to the device settings, also for booster channels, there are some addresses used for direct command inputs. 112 is for setting the track power of the module on or off. 113 is used to manipulate the polarity of the auto-reverse output, while 114 is used to reset the booster channel via the serial interface. 115 tells the booster channel to perform a short circuit current measurement, and 127 causes the booster module to send the entire list of configuration data to the serial port. All this data in the memory map can be accessed via the serial port of the Arduino using a set of JSON commands shown here. The JSON format is used because it is standardized and there are lots of libraries supporting it, so it is very easy to communicate with the booster from your own programs if you wish. As we see, the JSON sequence is structured in two parts. First, the command keyword CMD with a value of SV indicating system variables programming, which tells the booster that a command is sent to read or update the configuration. The second part is the list of parameters. DST for destination is the device or Loconet address. OPC for operation code is one of the opcodes from the list below. They are used to either read or write 1 or 4 bytes with each command. Adder for address has the memory location to be manipulated, and vals for values has the data that should go into that memory address. In case of a read command, the data in vals will be ignored, so the value does not matter. The booster will then answer with an identical command structure, only this time the command name is SVR, with the R standing for response. In the case of the write command, the response vals data will repeat the data sent to the booster, while in the case of a read command, the vals array will have the data of the specified memory location. The current operating status of the booster is reported about twice per second for each booster module using the DCC amp command shown here. It is just an array with the actual status values that then can be used to display short circuit status, overload percentage, and the RMS track current that is flowing through the booster.